Welcome back to our deep learning section of this computer vision course. Have you ever wondered how artificial intelligence creates stunning new images or accurately sees the world around us? It is not magic, it is deep learning, and we will break it down like never before. Firstly, we look at what is deep learning. Afterwards, we explore models such as convolutional neural network called CNN and generative adversarial neural network called GAN. We'll be looking at autoencoder, we'll be looking at vision transformers, vision language models, and a lot of practical application in this section. So take a seat and let's see what deep learning really is. So first, what is deep learning? It is a branch of machine learning that uses artificial intelligence neural network with many layers to automatically learn patterns directly from raw data. Instead of manually designing features, deep learning models figure them out on their own, starting from the simple edge in the first layer to shapes and corner and eventually the entire object in the deeper layers. That is why deep learning has completely transformed computer vision. Examples of these deep learnings are GAN, CNN, RNN, LSTM, DeepQ, autoencoder, variation autoencoder, and even graph neural network. See, let's look at some of the most important deep learning models. First, we start with CNN. Illustratively, every point in an image is a data point. Looking at this red point we have here indicates that at this particular point, the matrix or the number representing that particular image is what we represent here. So how does deep learning learn all these patterns? It learns from each layer, starting from just simple edge detection to shape until the entire complete image is realized. For instance now, adding a filter kernel, it multiplies the filter by the value of the metric position we are evaluating. Take for instance, we are evaluating this red part of the image. The filter added to this is 0, 1, 0, -1, 5, -1, 0, -1, 0. That's the filter value in 3 by 3. So the value we realize at this particular point will be our output value representation for the output image. Numerically, we are applying a kernel on a particular point in the image in order to realize our future map. We are placing this filter over the equivalent position and shifting them by one movement from left to right, then to bottom. CNN are backbone of modern computer vision. CNN work directly by actually scanning these small patches of an image, combining them and gradually learning spatial hierarchies of features. They are excellent at tasks like image classification, object detection, and even facial recognition. Whenever you hear about artificial intelligence detecting tumor in a medical scan or powering autonomous cars, it is CNN that is at work. Let's further look at CNN in a deeper level. We are placing a filter on a particular section of an image. After convolving this particular filter on the convolutional layer, we will arrive at a future map of a single position, which is what is illustratively here in the green area. Let's look at the architectures of CNN. So CNN here will be divided into three phases. The first is the feature extraction phase, where we have the learning blocks. We'll be having convolutional layer and max pooling layer in operation. The first convolutional layer in this section after the input layer is the core of the network, where it takes an input image, the example number 2 as written in the image, and slides this small 5 by 5 filter like a tiny magnifying glass over every part of the image. So we are sliding a small magnifying glass over every part of that particular image. What we are saying in essence is we are adding a 5 by 5 kernel over that particular image in order to get a shorter version of the image or a more stronger pattern of the image that gives us some important features. So the resulting filter creates one new map called future map. If we use an N filter, we will get an N feature map, each highlighting a different feature in an image. In simple analogy, it is like having a team of dictators where one dictators look only horizontal lines and the other looks at the vertical line. Next, we have a mask pooling layer behind the convolutional layer. Mask pooling layer does a downsampling operation. It looks at every area of an image and based on the mask pooling size, selects only the most significant features, that is, the number that has the highest value within a mask pooling operation region. I mean, it repeats the process of selecting important features using a 2 by 2 like pooling matrix over the convolution of 5 by 5, and this time the network learns more complex high level features like full shapes of the number or specific curve, preparing the data for the final classification level. So this mask pooling layer does it over and over again until it gets an accurate result. And the second layer as well, in the second layer, after the mask pooling layer is done selecting its own feature, the second layer repeats the same process using a 2 by 2 pooling layer on a convolve feature map, just as we did the operation in the first convolutional layer. The result this time around will learn more complex high level like and a full shape of number or specific curve, preparing the data for the final specification. So the next phase we're having will be a flattened layer. Here, the output from the final matrix of mask pooling layer in the second convolutional layer, as we have in the image above, we simply take all numbers and string them out in a single line. That is, it uses a function called ravel to convert the 3D feature map into a 1D vector, which is a standard input that is required for a traditional neural network. After this, we have the classification, which is the decision maker layer, where we have a fully connected layer of our neural network. And at this stage, it is the final operation of the convolutional neural network. It takes a long list of features and combine them, weigh their importance, and make final decision. After applying some activation functions like relu, the result we will be having of this network at this particular stage would be number labeled from 0 to 9. The number with the highest value of prediction will end up being the predicted value for the image input. The result of our node label 2, we have the highest score, making it the expected or predicted results from this particular operation. In summary, CNN goes from collecting raw pixels to complex features and flattening data before we arrive at our final prediction. Looking at a 2 by 2 mask pooling filter and a stride of 2. Stride is the number of steps we are making. We have a 1, 5, 1, 6 in the red region. If we are moving one stride, then the next phase would be 1, 6, 2, 7. That's one stride. If you are moving another one stride again, it will be 2, 7, 4, 1. But since we are moving two stride, was what give us capability to be able to move in 2 steps. Firstly, as we are done with 1, 5, 1, 6, we move a 2 step. That is, we will leave the 1 over 6 and move to 2 over 7. That's the second step we have previously. And that's how we were able to arrive at mapping a filter on the mask pool feature maps. At each region, at the red region, green region, yellow region, and blue region, we'll be selecting the most important features in mask pooling layer. Compared to its average pooling layer, which is another alternative example, it finds the average value of the entire region. Take for instance, if it's an average pooling layer we want to use, it will be 1 plus 1 plus 5 plus 6, which is 13 divided by 4. Our result will then be the max pooling value instead of 6. And that's how this operation works explicitly. Max pooling layer does a downsampling, while up pooling layer has the capability and ability to return the original features we fed into the machine. Take for instance, at this region, using a stride of 2 with 2 by 2 filter, resting them on each point or their expected map, will be arriving at 5, 6, 7, 8. At the point 1, the first one operation that was carried out was the 5, while the second one that was carried out was 2, the third one that was carried out was 3, which is 7 obviously, and the fourth one that was carried out was 4. So we will look at the position of that particular filter in the original extracted data, doing an inverse transformation. Then we will be fixing the procedural value, which is 1, 2, 3, 4, at their precise location in the output layer. From here, we will be able to arrive at the original fed layer or fed data into the model. This idea and modality is similar to an example of GAN. After applying a 3 by 3 stride, we see how the operation is being convolved. Firstly, 3 by 3 filter over this particular region will start from 1, 2, 1 down to 5, 4, 1, 4, 1, 2. Then it will move by 2 strides. That is, it will leave this particular region 1, it will leave particular region 2. Then the next area, which is 154, 137, 196, would be the next region of our calculation. Then we have a 3 by 3 future map extracted, which will be the second value that will be pushed into the next convolutional layer. We can have as many as possible convolutional layer depending on the type of operation or type of task we want to attain. Without wasting much of our time, let's dive into our notebook to see how deep learning works.